The recovery system on Lumineer is the system that failed. That's why the rocket crashed. Specifically this little piece of nylon. Today we're going to talk about how the recovery system is supposed to work and then how it actually worked. Thanks as well to today's sponsor, Grammarly. We'll talk more about them in a little bit. Let's get into the video. Lumineer was designed to use two separate parachutes to return to the ground after hitting apogee, a main parachute and a drogue parachute. You will see setups like this all of the time over high-powered rocketry and in the real industry. Crew Dragon, Starliner, New Shepard, basically anything coming back from high altitude, if it's not landing propulsively, it's going to use at least two types of parachutes. The point of the main parachute is obvious. You want to bring the rocket or payload down to the ground softly. The main parachute is usually larger than the drogue, which gives it a slower descent rate. But do you know what happens when you descend slowly for a long time? You drift sideways. Even with excellent wind modeling, drift can send you all sorts of places that you don't want to go. So how do you minimize drift in a largely passive system like parachutes? You cut down the amount of time that it's in the air. You just go down faster. And that's why we have a drogue parachute. The job of a drogue chute is to keep the initial descent of the vehicle at a manageable speed, at a manageable descent rate. We don't need to go super slow, but we can't be like burning towards the ground in a free fall. Drogue chutes can also be used to ensure the vehicle is in a specific orientation, pulling the center of pressure far aft of the vehicle, though that depends more on the application of like where the drogue is. Drogue chutes are designed to be, in most cases, deployed at high speed. When a Dragon capsule comes back from the International Space Station, when those drogue chutes deploy, the technical term for the amount of speed that capsule is at is really f***ing fast. But in the case of the rockets that I fly, because we're deploying at apogee, our speed should be zero, right? We want to deploy at the peak of flight when the velocity crosses from positive to a negative value, so the speed is zero, right? Hey, I don't know if you can tell, the speed was not zero. It was extremely not zero. The other thing a drogue parachute can be used for is pulling out a secondary chute. And sometimes this is called being a pilot chute, where the drogue chute, the force of it, will pull out the deployment bag of the next chute in the sort of chute stack. So for Lumineer, we did just this. We have a drogue parachute, a main parachute, and when it's time for the main parachute to deploy, we don't necessarily need to fire a second really energetic charge. We just need to cut a line so that the drogue parachute can then pull the main parachute out of the rocket body. I purposefully undersized the drogue parachute for Lumineer so that we'd have a fast descent rate. This was a 15-inch nylon parachute that was meant to be the drogue of the vehicle, and the target descent rate that we should have hit somewhere around is 45 meters per second. 10 kilometers is a very high way up, and we want to spend as little time in the air as possible after we hit that apogee so that we don't drift into the mountains nearby. This drogue chute was deployed using a piston in the center of the avionics bay, and in the bottom part of the piston, we had a little thing called a firebolt or a pyrobolt. These little things are homemade pyrotechnic bolts with a little bit of black powder in there and two redundant igniters. They get placed into the bottom of the piston, and when they fire, they pressurize this relatively small volume, putting a ton of force on the shaft here, getting the nose cone off, getting the chutes out, and getting the vehicle ready to come back down to the ground. The great thing about using the piston approach is A, it sounds really cool, and B, it can be adapted to use any type of pressurized or unpressurized gas. So CO2, nitrogen, just regular compressed air could all be very easily adapted to this system if we ever found ourselves in an environment where it was tough to fire or combust black powder. The piston method is also much easier to test. A core design philosophy of a lot of new space agencies is try to use as few pyrotechnic devices as possible, and this is because as you test a pyrotechnic device, you burn it. So you want to use a device that can be tested again and again to further characterize like repeatability and reliability. So the piston system, although heavy, was a nice choice sort of in that philosophy. These pyrobolts are actually a ripoff of something that the MIT rocket team does. The rocket team likes to call them firebolts. I call them pyrobolts. Doesn't really matter. We're talking about the same thing. I'll link their approach down below, but that entire wiki page they have is a fantastic resource for how they build their vehicles. I bored out most of a solid bolt on one end and then a much smaller hole on the other end. The smaller hole leaves room for the igniter wires to come through, and in order to make the system redundant, we have two separate igniters inside the pyrobolt, and either one of those can set off the black powder charge. The igniters are shrink-wrapped to prevent short circuits, and then a small amount of black powder is added. After that, the charge is sealed off with a little more heat shrink tubing. The charge is then epoxied into the bolt and left to dry. We're using the epoxy to create a sort of fake hermetic seal, and the goal is to prevent any pressure from escaping through the bolt when the charge fires. The seal doesn't need to be 100% perfect, but I took care to cover as much area as possible when assembling these pyrobolts. I had to experiment with a few different techniques for manufacturing these pyrobolts. I initially used totally loose black powder that was then sealed into the pyrobolt with CA, or cyanocrylate adhesive.
3, 2, 1. 3, 2, 1. Wow. Okay. Noted. 2, 1. 2, 1.
Apart from not having an easy to characterize come-up time, CA is inherently brittle, and you can guess how that might go in a high vibration environment. So I flipped over to the shrink wrap method and tested the pistons several times.
3, 2, 1.
So, with the mechanics of that covered, when the drogue is out, we'll use that drogue to pull out the main parachute. We'll do this by pyrotechnically cutting one of the lines that holds the drogue parachute on, and either of those pyrotechnic charges can be commanded by either independent flight computer. The target descent rate of the main parachute was about 9 meters per second, and we ended up with a 72-inch iris chute to get that done. Now, we're not technically doing a pyrotechnic cut of the line. There are pyro line cutters where you truly sever a continuous line. That's not exactly what's happening here. I'm using a device called a tender descender, and although this one is in very bad shape after returning from 10 kilometers, this is what it looks like. The general idea is that you fill a small reservoir with black powder and then you put the two pieces of the tender descender together. When you do that, you can put two quick links on either end and put a bunch of force in this direction without putting stress on that black powder charge. Then, when it's time to fire, we use two redundant igniters inside the tender descender to blow that black powder charge.
3, 2, 1.
That charge is going to blow these two pins out of the device. It's going to separate these two quick links, and then we're going to have that line effectively cut. And again, in the name of redundancy, we're actually using two parallel tender descenders. So either one of them can fail, either one of the charges can fail, and we can still get that main parachute out if everything works. Now it's time to make a lines diagram. And this is maybe the most important part of designing or assembling a recovery system for your rocket. Welcome to the whiteboard. I'm Joey B, and we're gonna make a lines diagram for Lumineer. A lines diagram is like a schematic. It's a way of representing what lines connect to where in terms of the recovery system for Lumineer. We're gonna start on the left. I'm gonna draw a little circle, and then I'm gonna complete it out and make it look sort of like an eye nut or an eye bolt. This is called the God nut. Why is it called the God nut? It's because if this thing breaks, it is time to pray. The God nut goes on the top of the avionics assembly, and it's where we attach all of the components of the recovery system. The chutes, the lines, the tender descenders, all those go directly into the God nut, and then the load goes through that into the airframe. One of the other things that I have here is going to be a quick disconnect, and this is going to be the primary quick disconnect. I know it doesn't look amazing, but this is the primary quick disconnect so that if we have to detach all of the parachutes, we can do that with just one device. It increases our risk just a little bit, but this makes integration and then modifications to the vehicle so much easier. Now, let's start in a reverse chronological order. I'm gonna redraw the God nut. I'm going to simplify this a little bit. The only thing that's going to attach to the God nut when we're close to the ground is the main parachute. So we'll draw this line, we'll call it the main, and then we'll draw out our chute here. Very good at illustrating. I am a world-class artist. So that's our main chute. When we're coming down, this is our landing config. Landing. But we spend most of our descent under the Drogue parachute. So I'm gonna draw that here. I am an excellent artist, just absolutely incredible. We're gonna label that D. This is M for main. The Drogue is also connected to what? It's connected to the nose cone. Look at how good that nose cone is. It's obviously to scale with the God nut. This is an excellent diagram. I'm also realizing I probably shouldn't have chosen green as the color that I do this in. It doesn't show up that well, but oh well, we're already doing it, so. The first attachment from the Drogue is going to be called the Drogue riser. The riser is going to separate the Drogue a decent length from the vehicle. The Drogue riser is going to connect through sometimes a separate line called the Drogue unloader, and I'm just gonna label this as U. The reason we call it a Drogue unloader is because we're unloading the main parachute in the main bag, because in this configuration when we're following, we still have the main parachute, it's just in the bag. So let's draw that. This box right here is going to be the main parachute, and I'll draw a little squiggly line so that you know that that's the main parachute coming out of the bag. So I'm gonna say MB for main bag. Now the top of the bag gets pulled. That's how the main parachute comes out. The parachute's stuffed in this little bag, you pull on the top of it, the parachute comes out. So the top of the bag is connected to the joint between the Drogue unloader and the Drogue riser. My gosh, I'm tongue-tied. Now we can make a super easy addition here. The main bag also houses the main parachute. The main parachute we know needs to be connected to the God nut, so let's make that connection now. I'm also gonna get rid of the quick link here. We don't really need to represent that, and I kind of need a little bit more space. So here we go. That's connected to the God nut. That's the main parachute right there. You'll see this a little bit later in the video. One of the modifications we made, I'm gonna represent with just a line here. And this is a hair tie. Specifically, it's Xyla Foxlin's hair tie. Thank you, Xyla, for lending this. It turned out to be a flight critical component.
So we just do this, and so we don't have the lines running through it, but we have it like here, and then we have a line such that this is tied.
It pulls it out.
Yeah, this is tied to something on the TD loop. So this is a fixed length, and it's like loose until there's.
I love it.
That's brilliant.
Yay! I love it.
Yes!
We have a hair tie that goes around the main bag because as this bag is flapping about on the way down from 10 kilometers, there's a really high chance that this main parachute could unfurl. So we want to prevent that. And we have just a little bit of force from that hair tie that keeps it in. So the concern is that the main will untie.
So like if we just flop around, like if we just.
That's coming out.
Yeah, it's gonna come out.
I hate that. The way that the hair tie separates from the main bag is when the Drogue riser pulls the bag off, and the hair tie is also connected to the God nut. So these things get pulled in different direction. The main bag both opens so that we can get all of the lines from the main parachute out, and then the main parachute comes out of the bag itself.
Yes.
All right, yeah.
Sorry, beautiful.
Cut.
Beautiful.
Now we still haven't connected the Drogue to the rocket itself. We have this unloader, but how does the unloader get to the God nut? It gets there through the tender descenders. I'm gonna draw these as two different boxes and labeled them TD, and each tender descender has an upper loop and a lower loop. Here's the upper loop, and here is the lower loop. The lower loop is gonna connect directly to the God nut, and I'll just draw a link right there. I guess we'll draw that quick link back in there. But the upper loop is what we want to disconnect. So as we're falling from 10 kilometers, we've got all of this drag from the Drogue parachute, and it's going to equalize at some point to where the Drogue is pulling just enough that we reach some terminal velocity. The load goes through the Drogue riser, then it goes through the Drogue unloader, and it's important to note here, the reason we have this unloader, specifically, this is sized so that it is shorter than all of these lines together, because we want the load to go through there first, not at all through the main bag, not through the main parachute, through nothing. If we were to start pulling on the main bag, that main parachute's coming out early. So the Drogue unloader then sends the load through the tender descenders, which go through this quick link, which go into the god nut, which goes into the rocket. And that's how we attach the Drogue. Let's say that just one tender descender works, not two. It's a redundant system, so if we were to break the top one, if the first one separates, we have this line, which is going to slip out, the unloader is going to release, and then it's going to put the load into the main bag, which is going to pull out the parachute, pull back the hair tie, and will separate cleanly.
And you can just...
All right, 3, 2, 1, set.
Yep.
So that pulls, it snaps, the bag comes off.
What if both tender descenders fire? Here's a problem. We have this line, which isn't attached to anything, right? Well, we can attach it to the main bag. The main bag actually has a separate line that goes right through here, and we can attach it to this line somehow. But what happens to the tender descenders? Those tender descenders need to have loops on them that attach them separately from the tender descender main loads. So we put those through this quick link right here. We have this line accounted for, we have the main bag accounted for, but then even still, we're dropping stuff in the desert. Because what happens to this Drogue, nose cone, Drogue riser, and main bag? They're just going to fly away. They're no longer attached to the vehicle. This is the solution we ended up settling on for Lumineer because we couldn't get everything to fit in the vehicle. And so what we did is we did some dispersion calculations based on the ground level winds, our deployment altitudes, etc. If I'm remembering this correctly, we found that the Drogue and the nose cone and the main bag should land somewhere within a 200-meter radius of the vehicle, and that was small enough that we were like, all right, cool, we can just search for this thing. But if you were coming down and deploying your main at a higher altitude, this wouldn't be such a viable solution, or you'd have to accept that all right, we're just gonna litter the desert. Another way to do this, and this is how Lumineer was originally designed, was you can take part of this joint right here between the unloader and the Drogue riser, and you can add another line. I'll put a little squiggly there so you know that it could be a lot longer. You add another line to the god nut so that the Drogue can pull out. All of these things can pull out, but this line is the longest of them all. So by the time this line becomes taut, you've already pulled out the main parachute. And then so when you descend, your rocket and recovery system, every part of this comes down as one piece. This is already crazy simplified from how we actually flew Lumineer. Mostly what I wanted to do here was show you that it's very important to draw out a lines diagram and think of what happens if both tender descenders fire? What happens if just one of them fires? What happens if they fail? Where do the lines become taut? Where do the load paths go? Parachutes are a difficult problem to solve that will be made so much worse if you don't plan out what connects to what on your rocket. So, with that all covered, we can go back to the desk. All right, with the lines diagram made, let's talk about the mechanics of the initial Drogue deployment. To get the Drogue out, we have to get the nose cone off, and to get the nose cone off, we fire that piston. The piston is attached to a flat aluminum plate, which is attached to the bottom of what we're gonna call a cup. Now, the point of the cup is to hold the main deployment bag, the main lines, the tender descenders, and a bunch of things, but I did a terrible job at forethought here, and so I way undersized the cup. With the amount of Kevlar line that we had, the bulk of the tender descenders, the bulk of the main parachute bag, it could not fit in here. And frankly, I'm just gonna take the L on that. I did a really bad job planing this. The cup sits right below the nose cone in the airframe, and it's the same diameter as a coupler tube inside the airframe. So when the piston fires, the cup, with all of this chute stuff inside, pushes the nose cone out from the coupler on the nose cone. The nose cone comes off. The weight of the nose cone pulls the Drogue parachute out just far enough to inflate, and then the weight of the Drogue, or rather the drag of the Drogue, pulls out any other parts of the recovery system that need to come out at that point. A few things about the nose cone though. We're going to use something called shear pins to keep the nose cone attached to the vehicle. And the first question might be, Joe, why do we need to keep it attached? Well, here's the thing. As you go up to 10 kilometers over the course of 45 seconds, that's a lot of drop in air pressure for a relatively short amount of time. And if you've done a good job sealing off your avionics bay, guess what's going to happen to the pressure differential between the inside and the outside of your rocket? If you go up fast enough, the inside of your rocket is going to have a high relative pressure in comparison with the outside, even if the seals between the two aren't perfect. What this means is that there is a total potential, and it's a real problem, it happens to Rocketeers all the time, that you pop the nose cone off on ascent because of that pressure. You have to vent it on the way up. And that's why you see vents on the side of the fairing on, for example, the Falcon 9. If you look at these vents around the edge, they are all placed there to aid in equalizing the pressure quickly between the inside and outside of the fairing. So we're gonna do the same thing, we're just gonna do it in a far more sketchy way. I took a drill with about a 1/8 inch bit, I drilled 1, 2, and 3 holes, and I said, that looks good enough. The other thing that happens is when your motor burns out, sometimes there's a pretty solid kick in the system that sends internal parts of the rocket careening forward. You don't want this, it's not an excellent thing, but if you think of the chute assembly, there's nothing that rigidly attaches the parachutes to the vehicle. They're just sort of sitting in there loose. So you do want a little bit of forward retention so the nose cone can't come off until you really push it off. And that's the job of the shear pins. So I drilled 4 holes around the airframe for the shear pins to keep the nose cone on, and they do exactly what they sound like. They shear. They're designed to shear along the, gosh, I don't know how to describe it. They're shear pins, they break. In order to make sure that these shear pins would work, I also ran 2 different deployment tests on the ground before I left for California, where we actually flew this thing. The first test, we just popped off the nose cone, and I wanted to see if the shear pins would break with that amount of force. 3, 2, 1, fire. Nice. The second test, I did add some parachutes in there without a proper lines diagram or proper setup, but again, just wanted to simulate as close as possible to the actual thing. And at this point, it was time to head out to California, and in the interest of transparency, here is a quick little disclaimer. We got a house out in California with a bunch of rocket folks, a bunch of my friends. About 80% of us were fully vaccinated at this point. Each of us got tested for COVID before, during, and after the trip. We settled on an approach that felt safe to us and felt relatively responsible. This, and in future videos, is also where things start to go a little downhill in terms of the language we use. It was a very stressful 2 weeks, and you have been warned. The first day we were out at the launch site, I was unable to fly Lumineer for 2 reasons. The first had to do with some details on the certification process for getting my level 3. That was the point of this vehicle, to get the L3. For a lot of different reasons that didn't end up happening, some of them were regulatory, and then the second reason we didn't fly is that I just was not ready. I did not do a good job preparing for this first flight attempt. We showed up to the launch site with the vehicle in pieces. We were running the L-1 checklist on L-0. Things were not good. I then got heat stroke and sat in my car for an hour and a half to try to rehydrate, and then helped other people fly their rockets instead. With that covered, here is a recovery system focused view of what we went through on L-1 for the second attempt. All right, so nose cone goes at the end of the Drogue riser. I had it not somewhere around here, and it wasn't quite high enough, and I don't see any downside to keeping the Drogue really close.
After the pull test, make a lines diagram.
Yeah, we need to update the lines diagram.
There is no lines diagram.
No, it's in my dog, but it's old.
Oh.
Yeah, it was also just never quite right, and we worked it out on a phone call, and I'm like, hey, you should update that, and then I sort of think that was not a critical path.
Yeah, I definitely meant to update it, and then everything else happened.
Like I said, not critical path. Wow.
What
is the load rating on these quick links?
500 pounds? I mean, okay, here's the thing though, Sam. There's no shock loading on the tender descender quick links. There's not a
Drogue opening, question mark?
Drogue opening is not going to happen that fast. Ah! That is literally what killed the flight, you idiot. It's helpful to have footage of your opinions in the past, just to see how wrong you are. That's all. Go back to the video now.
Like in a nominal flight case, your apogee deploy velocity is 0. It doesn't take a whole lot of off nominal case. Like Therion deployed its chutes at over 100 meters a second, and it only went to 10,000 feet.
Uh-oh.
Maybe I should be telling horror stories now.
Oh no. Chutes make me nervous, man. Go up. Start threading these in.
We just need to find a home.
I'm starting to get good
at
the nose cone insertion, actually. Hey guys, welcome back to Joey B Rocket Reviews. Today we're unboxing a parachute that's inside of this rocket. Don't forget to like, comment, subscribe. I have new merch. You can get 1.5% off if you use code JoeyB at checkout. joeyb.com/gov.shop. Check it out.
Yeah, just Yeah.
Oh, wow. So the concern is that the main will untie
So like if we
itself.
just flop around, like if we just...
That's coming out.
Yeah,
Yeah.
it's gonna come out.
Because it's not like there's any force pushing it out. It's just like if we, or dental floss. I have the dental floss. That will rip when we, I mean, I don't know.
Let's go get some dental floss. And let's do some brake tests.
Okay. Yeah. What would happen is that the Drogue still acts as a pilot. It pulls the main bag entirely off. But the reason we would want to yeet the line for the Drogue
Is because then we can pack the main into the cup.
because it can get really tight in there
Yeah, so we can put that line entirely on top of the Drogue.
instead of flopping the Drogue lines around.
In the right spot. And you're like, what's this loop for?
That's exactly how I sound. That's a really good impression of me. Almost there. Xyla, do you want to explain what's happening here? Like what you're doing?
Arts and crafts.
The deal is that we need string/rope, and we are Rocketeers, so naturally we didn't bring any extra.
Okay, I've got the nose cone. Oh,
That's
we
okay,
no longer
that's okay.
have a cup.
That is okay.
Can you imagine doing this?
Who designed this? Is my face ready yet?
Yes.
Here we go.
Have you tried hitting it harder?
Go harder. Ah.
Go flight.
Oh.
Okay, so the nose cone comes out. We're gonna do this slowly.
Yeah.
That's the Drogue.
Keep
out.
walking with the nose cone.
That's it with the nose cone. So
So-
this is gonna flap around.
Yep.
It's so that I can simulate
Yep.
a deployed tender descender.
Yep.
So we're gonna deploy one.
Yep.
All right, 3, 2, 1, set.
Yep.
So that pulls, it snaps, the bag comes off.
Okay, now let's pack it for reals.
Okay, and so,
Hair tie.
I will go get you another hair tie.
okay. Thank you, Xyla. I'm f***ing yeeting you into the sky, and like, you can come back if you want.
Oh yeah, we just need to take
How do you feel?
This is a really small taste of that whole day, and in fact, in that whole week, there must be like 6 to 7 hours of just raw video from that. I find it very interesting. I don't know that anyone else would. I'd be fine with publishing it, but I just don't know that anyone's interested in watching that much of just like us losing our minds. If you have an opinion on that, let me know in the comments. With all of the parachutes troubleshooted and the pull tests complete, we put the vehicle together for final integration. We took an immense number of closeout photos for this process. Closeout photos help you troubleshoot anomalies after they happen. They're photos that are taken right before something goes into the airframe and you never see it again. They happen for satellites, they happen for launch vehicles, they happened here, and they're a great idea. Dude, I don't know why I didn't film this before, but I want to give a massive thank you to Andrew Adams, Charlie Garcia, Jenna Kay, and Xyla Foxlin. All 4 of those people carried me through that last week, and especially that last day. I've been doing the one-person, like, Joey B. launches model rockets things for a while, and I went into HPR thinking I could do the same thing, but you just can't. You cannot launch something like this alone. You need a group of friends or a group of people who are willing to help you, and every single person in this photo stepped up and did that. So thank you so much to all of them. And at this point, in terms of the recovery system, there was nothing left to do but just launch it.
2, 1, ignition. All right, that's a good burn so far.
The launch looked great initially. We had a good connection to the vehicle, and then as we passed around 4 kilometers, we started to lose telemetry altogether. Ava continued to record data and work just fine, which is the data that you're seeing displayed on your screen now, but we had no idea on the ground where this thing was, what it was doing, and why it wouldn't talk to us. We'll discuss the problems with the telemetry in the next video where we talk about avionics, but this was really bad, maybe worse than the recovery failure. But we're not talking about that. We're talking about the parachutes. So here comes apogee, around which point the telemetrum flight computer, that is the little green one right here, fires the charge about 0.2 seconds before Ava tries to fire it. That type of time is never going to make a difference here. Telemetrum just got to it first, but you can see that Ava sends the pyro command, so that's great. Both computers were working just fine. Here's where I start to have a little confusion, and we start to just look at the pixels as close as we possibly can. The Drogue deployment initially looks good, and we see a full inflated chute. The chute intentionally has a hole in the center, and I can't see anything that looks wrong with it. Then the vehicle rotates around a little bit, and we get another view of the chute. At this point, when we see it, it's either tangled up or it's starting to rip apart. My theory so far is that the chute inflated okay, and then the shock of the vehicle whipped it around, pulled on the chute really hard, and that ripped it. Additionally, we could have had an initial tear that is just not visible in this camera that then propagated more and more on the way down. And then we start falling, and we start falling in the way that we want, which is somewhat of a flat spin. The drag of the vehicle itself is roughly equal to the drag of the nose cone and the drogue. So instead of falling with the vehicle coming down like that, the vehicle's sort of flat looking out at the horizon, and the two of them are falling together, sort of like that. I was only able to recover 1 out of the 4 cameras, and the down-looking camera is the only one we have, so we don't get a lot of good glimpses of that drogue parachute. But we can look at the data and infer some information about it. So when we're coming down, we go through 3 phases where we go stable nose down as opposed to a flat spin. During the flat spin portion, we average between 40 and 45 meters per second of descent rate. I mentioned earlier that the drogue is sized so that we should have been at about 45 meters per second. To me, that tells me one of 2 things, and I don't know which one is correct. You'll have to let me know if you have a better sense for this. I simulated using OpenRocket, and I do not know if OpenRocket is also simulating the drag of a flat spinning body. If that is the case, then it looks like we have a drogue that's working, because we are flat spinning and we are hitting that descent rate that we think should be correct. If OpenRocket is only simulating the CD of the chute itself, the coefficient of drag, that means our chute is ripped, and that is sort of what my mind tells me is more true. An intact drogue chute should give us a descent rate that is slower than 45 meters per second if we also have the drag of that body falling flat as well. Those 3 stable nose down periods though, they tell me that something else is going wrong. They tell me that the drogue chute does not have enough drag on its own, and I am pretty sure this is not a design decision. I'm pretty sure this is also indicative of a drogue chute that does not have a high enough coefficient of drag because it is no longer a chute, it is more of a, well, this. So at this point, falling down, the drogue doesn't have enough drag to keep the vehicle in a flat spin orientation, and we go stable nose down. This also makes sense because the fins on Lumineer are large enough that we had a high enough stability caliber that we could go stable without a nose cone. The stable nose down periods, though, were a blessing and a curse. As mentioned, we had a lot of trouble getting telemetry from the vehicle, and at this point on the ground, I'm assuming the worst. We hadn't seen any puffs on the horizon, so we didn't think it came in ballistic, but we just had no idea where it was. But thanks to the failing recovery system, we had one of these violent reorientation periods during stable nose down. Somehow, the polar pattern of the antennas on the vehicle lined up with the polar pattern of the antennas on the ground, and we got like 3 or 4 packets of full telemetry from Ava through to the ground, which gave us GPS coordinates, descent rate, a little bit of vehicle information, and just enough to let us find this thing.
What time? What is our VOT? The top right.
VOT top right is 4801.
It's just stuck.
Yeah.
So it is possible that we are okay, and it is very possible that we are not. Stay in the bunker, please.
Oh yeah. Velocity is negative 60 meters a second. We appear to have drogue deploy.
That is consistent with drogue deploy. Oh my god.
Finally, as we continue going down, the air pressure keeps increasing and we hit a 3rd stable nose down period. This is the period that officially kills the rocket because at this point the air pressure is high enough that we're just stuck in that nose down orientation. We're not really going to get kicked back out. So as the vehicle is careening downward at 80 meters per second, we plunge into the desert floor. It's also during this stable nose down period that 2 important things happen. The telemetrum and Ava were both still online, working, feeling great, and trying to deploy the main parachute. When we found the vehicle on the ground, these are the actual tender descenders from flight. Both of them are charred with black powder because they both fired, and we can see that firing command on Ava as we pass our firing altitude. The problem is, this doesn't have enough drag to pull a parachute out of the rocket. The chute failed as a pilot, and then we don't have a pilot to get the main out. It's also clear through video that the main was getting kind of tangled at this point, and frankly, our chances of getting this thing to inflate were relatively low. One of the funniest things to me here, maybe funny is the wrong word, is that it really looks like the main chute almost did deploy. Like, it looks like we almost got to a point where we could have safely touched down. If you look at this footage right after we found it, obviously it's in this kind of crater in the ground, but that main parachute is like, I don't know, it's like partially open. Yeah, so here's the main. It is still sort of in the bag. Okay. Just trying to get
the TD's fired. Let's figure that out.
Yeah. They look fired.
Is TD fired? Oh,
Yeah.
and they're separated, so they had to have fired.
When we found it, the chute was still mildly stuck in the bag, but was about halfway out. I think if we had jostled a little bit more, or maybe the vehicle was a little lighter and had a longer descent, it's possible it would have come out, but it would have been through sheer dumb luck, not because we did a really good job like engineering this thing. I'm gonna toss the combined data view up on the channel as a separate video, and there are a few more videos that are coming out as part of the Building Lumineer series. We'll do one that's all about motor integration, we'll do one that's all about avionics, we'll do one that's all about the launch day logistics. But thank you for the patience, as I know these videos come out a lot slower than I intend them to. And now I'd like to thank the sponsor for today's video, which is Grammarly. Grammarly is a digital writing assistant which can work in a few different places, including as a desktop app or as a browser extension, which is pretty handy. You can create a free account which will automatically check your punctuation, your spelling, and maybe, as you might guess by the name, your grammar. For me personally though, I find Grammarly Premium to be the most helpful, as it helps you get far more clarity in the text that you're trying to write. I have a lot of trouble with this personally. I create run-on sentences, I'm inefficient in the text that I write. It's evident in the pages and pages of scripts that I write for these videos, but Grammarly has helped me cut that down to just the essential, well-put information. I also use Grammarly on a bunch of internal and external BPS documents and instructions where I'm trying to specify to a reader how to assemble something. And if there's one place that you really want clarity, it's in documentation, it's in instruction. As a tool, it has consistently helped me write instructions which are far more clear than they would otherwise be. You can save time on your work and emails with Grammarly. Go to grammarly.com/BPS to get a free account and 20% off Grammarly Premium today. It'll help you save time and work more efficiently. So thank you to Grammarly for sponsoring today's video, and thank you to you for watching. Thanks as well to the patrons who help support this project. I could not be doing any of it without them, so thank you very much. That's all I've got for now. I'll see you in the next video. My name's Joe Barnard. May your skies be blue and your winds be low.